Hello, Science 30s. This is the next lesson from the physics unit. So we're through all the field stuff that we have so far, and now on to current and electricity, and we'll get into some circuit stuff as well. So I sent you out a whole bunch of additional support videos. You'll notice most of them are actually from Crash Course, and it's that wonderful lady discussing a whole bunch of different things. So it looks like it's Crash Course Physics, probably somewhere around 24 through 33-ish, or really hot items within this physics unit. And again, these are huge, huge, huge topics that we only barely get to touch upon. So if you were taking, I don't remember, I think it's in Physics 30, we would be spending a ton of time on this sort of stuff. So we really only graze the surface, and that doesn't make it easier. That just means that we don't have kind of the deep understanding. So I would definitely watch those videos and even watch them a couple of times just to solidify some of these concepts because they are quite complex. But again, these things we're going to go through so quickly would be usually in like a pure physics course, you'd spend a lot of time on it. So these three things, kind of four things that we're going to go through today, oh my gosh, it's a lot. Um, well, it's not a lot in my course. I just realized I don't have my pen. But there's a lot of information that can help you kind of support it. I've just got to go find my stylus. Hang on. All right, I think we're good to go. Now I also need to tablet my computer. Woo. So, current electricity. So this will relate back to some of the electrical field stuff that we saw in the fields portion. Um, and we'll see how it kind of ties to the next couple of lessons as well. So whenever electric charges move, a current is said to exist. Of course, all the stuff going on. So a current is said to exist. And again, when we're talking electric charges, um, quite often we're talking about the movement of electrons. So electric charges, so what we can usually represent it is electrons like moving through a wire. So just representing there E with a negative, electrons moving through a wire. Um, and so our definition for current, so we've said that there, and you probably have kind of a visual of what you think current would be. But current is the rate at which charge flows through a surface. So again, rate, usually when we're talking about rates, it's something per unit time or something like that, or per another quantity. Um, so here, I also want to check what we have formula-wise in our data booklets. You might need to peek at your data booklets to see what we actually have for these formulas. Of course, again, I don't have what I need in front of me. There we are. So this stuff should all be on, or I guess this one, I it's not in this form. It's one of kind of the derived formulas that you'll have. So you might see these come up. I think with the Explore Learning, you'll see some of these formulas come up. So this is the Explore Learning is that applet that we're going to use later this week. So some of these formulas might kind of come up again. So our formula for current is I equals Q divided by T. And again, if you've already watched the Crash Course videos, you would have seen this formula. Um, and you'll see that we do some kind of inserting of one formula into the other a couple of times. So I equals Q divided by T, where I is defined as the current measured in amperes. Q is the charge measured in coulombs, just like we had before when we were looking at our electric field strength. We used Q before, again, as the charge in coulombs, and time in seconds. So this is a rate because it's saying charge per unit time, per second. So again, it's the rate at which charge flows through or across the surface. Um, and so 1 ampere, 1 amp, it usually is how we end up writing it. 1 amp is equal to 1 coulomb per second. So that's what 1 ampere is actually. So current, we'll see that current is really important when we're getting into induction. So we'll look at magnetic induction, and that requires current to be flowing through a wire, and it can also cause heat. Current is kind of the cause of heat within wires. So the SI unit of current is the ampere. We already said that. Usually represented by a capital A. Oh, I see that I'm writing all the things that I have. So 1 ampere is equal to 1 coulomb per second. 1 amp of current is equivalent to 1 coulomb of charge passing through a point in a time interval equal to 1 second. In a metallic conductor, so we know for the most part, metals are pretty darn good at conducting electricity and allowing the movement of those electrons to occur. So in a metallic conductor, the current is due to the motion of the negatively charged electrons. The direction of what we would call the conventional current is opposite the flow of the electrons. And so again, I'll keep referring back to these crash course videos because they just really represent what would be opposing, or what that would actually represent. So that's what we call the conventional current. So it's opposite the flow of the electrons. So if you're thinking about the positive, what that would actually represent. Sorry, I need a drink. That was probably loud drinking sound, and that's super gross. I'm sorry. Conductors are materials through which electric charges can move. Oops. I tried to slide my screen. No luck. Charges can move under the influence of electric forces. So anything that conducts electricity here. So like we said above, metals, real good at conducting electricity. In Science 10, when we talked about ionic versus molecular compounds, ionic compounds, when in solution, are great conductors of electricity, again, because they form those ion species. They form those positive or negative ion species, so they will allow the flow of electrons within that. Insulators, on the other hand, are materials that do not readily allow charges to move. So they're not good conductors. Typically, we'll call them insulators. So something like wood, not a great conductor of electricity and heat. Plastic, also not best. Just like we said, ionic compounds are really great at conducting. Molecular compounds are not. And again, that's because they don't form ions in solution. So something like glucose, C6H12O6, remember that those bonds are formed, they're called covalent bonds, and they're formed by the sharing of electrons. They aren't formed by the transfer of electrons. So within solution, they don't actually dissociate into ions. So they are not able to conduct electricity. So that is what is happening in terms of current. So again, current is a rate at which charge flows across a surface or past a point in a certain time interval, whatever our time interval would be. So we need to understand current in order to do some of the calculations with Ohm's law that we're going to look at. So another piece of information that you've probably heard of before, but maybe don't understand what that necessarily would mean, is the word voltage. So back to Science 10, when we started to talk about energy, we said energy is the ability to do work. So we would have looked at kinetic energy and potential energy and how that is the ability to do work. And we defined work as force times distance, but we don't really need that one right now. So energy can exist in many forms. Again, we did a whole bunch of this stuff in Science 10, but we have thermal energy or heat. We have light energy. We could write so many different things. You guys have looked at other energy forms, something like nuclear energy, a whole bunch of things. Since we're talking about it though, let's call it electrical energy. And again, electrical energy is a type of kinetic energy because it involves the movement of electrons. So electrical energy is the energy contained in charged particles, and voltage is the work done to move a charge from point A to point B divided by the magnitude of the charge, so how big the charge actually is. Voltage is often referred to as electrical potential difference. I don't know if I can fit all that. I think in those crash course videos, they usually just say potential difference, but it's your electrical potential difference. So the SI units of voltage are known as joules per coulomb, which is more commonly written as a volt. It is a joule per coulomb. 1 joule per coulomb is equal to 1 volt. And you've probably heard of something like a 9-volt battery, right? Those are kind of the big, not rectangular prism, I guess, batteries that you can use. And so again, that's talking about the voltage. And again, that's the potential difference. So our formula for voltage is EE, which is our electrical potential energy measured in joules. Energy is always measured in joules. Same with work. Divided by Q. And again, that's the magnitude of the charge. So not just positive or negative, but the magnitude, the number related to the charge. And that will get us our voltage. So yeah, you've seen voltage ratings on different items. Something like battery is a really good one. So batteries are the sources of voltage when we're talking about electric circuits. When we start to look at circuit board stuff, the voltage, the potential difference, the electrical potential difference, is supplied by the battery. So current will flow from higher to lower voltage. That's something that's important. If you think kind of like transport stuff that we did before in Science 10, where we said things will diffuse from higher concentration to lower concentration. Current is kind of the same way, that it's going to flow from a higher to a lower voltage, unless there is a source of energy to push it in the reverse direction. So that's something that, again, comes up in that video. I've said it enough. Maybe you're tired of listening to me say it and you want to just go watch it. So you might need to do that. Sorry, I'm just peeking at my notes to see what other little notes I wrote myself. So the more batteries you connect, the more voltage you'll get. The higher the electrical potential difference, depending on how many batteries you have in series. Again, we'll get to that with circuit stuff. So measuring volts and amps. So the way that these can be measured. So these ones are pretty easy to remember. So the way that you measure voltage is a voltmeter. So it's used to measure voltage and detects the difference in potential caused by a device in the circuit. Therefore, a 6-volt battery, I was just talking about 9-volt batteries, but I guess we're talking about 6 now. 6-volt battery measures a potential difference of 6 volts from the positive to the negative terminal. I know we haven't really talked about this part yet. We'll do series versus parallel. I don't think tomorrow, but I don't remember what order everything goes in. So voltmeters must be connected in parallel across the device. And then when we're measuring current, so again, current is measured in amperes, so it's measured by something called an ammeter. So it measures the rate that charged particles pass by a specific point. Ammeters, that's the difference to voltmeters, need to be connected in series. And again, we'll do series versus parallel, but I guess I just added it in there. So those of you that are rocking in yoga class right now, I don't know, whenever I'm in yoga and they tell me to do my ohms, I always have a little bit of a giggle where they make you go om and you hold it and you just sit all zen like. I always have to think of Ohm's law, relate physics to, you know, trying to be zen and tranquil and one with the universe. I have to think of physics instead. So George Simon Ohm, so in the mid 1800s, was the first to note that the current in a conductor is directly proportional to the applied voltage. So again, thinking about those terms, so current is looking at the rate of flow of charged particles past a point, and voltage, if we're talking about voltage, again, it is equal to your electrical potential energy divided by the magnitude of the charge. So he proposed this formula, and so I don't know where. Oh, I was like, I'm missing a part. So I don't know why it disappeared off my sheet. I don't know if it's on yours. So I is equal to the current, again measured in amps. That is that's the same symbol we used on the last page. So this first formula, so these are in your data booklet for sure. So V equals I multiplied by R. So that's saying the voltage is equal to the measure of your current multiplied by the resistance of um, whatever is within the circuit. So we haven't really talked about resistance yet, but resistance is measured in ohms. So this is omega, I believe that's omega. And it's, you can't really see it. I always just get lazy. I think it's supposed to have a little hook at the front and go like this, and have a little hook at the back. I was just writing it like that. So resistance measured in ohms. And so resistance is a measure, so again it's using R there, is a measure of collisions between electrons and atoms and has the unit of ohms. So it's looking at how many collisions there are within that flow of electrons and whatever is within your circuit and has the unit of ohms here. So current increases as voltage increases. So if we're looking at that formula, if I increase this, well, this also has to come up. We can't really change the resistance of the circuit unless we add something different into the circuit. And again, we haven't done our circuitry stuff, so that might not make a whole lot of sense. But if we increase the amount of current, that's going to increase the voltage. If we decrease the current, that is going to decrease the voltage. So they're directly, that's what we call directly proportional. So I don't know how to write that there, but I guess I can write it for this part. So current decreases as resistance increases. This is something called inversely proportional. I think there's an E there. So that's saying that if you increase the resistance, that's going to decrease the current. So again, decrease the flow of charged particles past a point per unit time if the resistance is increased. So if you increase one, you're going to decrease the other. Recognize B9. I don't even know what that means. And so, is that all I have? Yeah, just some kind of practice questions based on that formula. You might need to use some of the formulas from that last page, so either looking at your calculation of current or your calculation of voltage. So let's look at some of these questions. And again, this one's in your data booklet for sure. I didn't see the other ones. V equals I times R equals P times T. Sorry, I'm just doing a little search around. Okay, we'll get to some of the other formulas when we get to the power stuff. We don't need that quite yet. So this is Ohm's law. Ohm's law. So a light bulb with a resistance of 10 ohms is connected to a battery. If the current in the light bulb is 0.6 amps, what is the voltage of the battery? So just like usual, I always write out the pieces of information that I have. And again, don't forget that in your data booklet, it has the formula. And it also has each of the variables defined there and what units you use. So if you're like, I can't remember what this is if it didn't say the word resistance here. If I couldn't figure out what that actually is, you could look in your data booklet and it tells you that that is a resistance. So I see that I have my current equal to 0.6 amps. I have my resistance equal to 10 ohms. So now substituting in V equals I times R. All right, I have I have R. I'll be able to calculate voltage. So 0.6 amps multiplied by 10 ohms. And so again, having a unit of amp ohms, I guess technically that would be right, but the unit that we always use is volts for voltage, which is nice and easy to think about. So 0.6 times 10 is 6. Yep, just one significant digit for this because this question or this portion of the question only has one significant digit. So it would be 6 volts is the voltage of the battery. So again, that's looking at your potential difference per whatever the magnitude of the charge is that's flowing. So the next one, it says a steam iron states that the iron carries a current of 6 amps when connected to a 120 volt source. So I believe most of our electrical outlets are 120 volts, but I could be wrong. So again, writing out the pieces of information that you know. Current I equals 6 amps. Voltage equals 120 volts. What is the resistance of the steam iron? So that's question mark ohms. So V equals I times R. So in this case, we need to rearrange the formula to solve for R. So we need to rewrite the formula so that it's R equal to something. So if I'm trying to rearrange this formula to solve for R, I know that I need to deal with the fact that it's right next to I. So right now it's I multiplied by R. So I know that I need to divide both sides by I to solve for R. So V divided by I is equal to R. And so now I can substitute in the known values that I have. So 120 volts divided by the current, 6 amps, gets me 20 ohms. Looking at my question though, I see this has only one sig dig. So I can't just be like, okay, I guess I'll just drop the 0 because 2 is basically the same as 20. It is not, but I could write it in scientific notation as 2 times 10 to the power of 1 ohms. And this is with my correct number of significant digits. because in scientific notation, only your coefficient counts as significant digits. Again, what I've done is I've moved this decimal one spot over. Okay, so the resistance of a hot plate is equal to 40 ohms. I'll write that out. How much current does the plate carry when connected to a 120 volt source? So in this case, now we're searching for I. We're trying to rearrange the formula to solve for I. Right now I have I multiplied by R, so I need to divide both sides of the equation by R. So now I will have V over R is equal to I. Now I can substitute in my known values. 120 volts divided by 40 ohms. That looks crazy. So 120 divided by 40 is 3 significant digits. I have 3 there, I have 2 there, so I actually want to write it as 3.0 amps. So, again, go watch those crash course videos. Yes, I think there's probably about 8 of them that are helpful, and they're all 10-ish minutes, so you have a little bit of a commitment. You don't need to watch them all right now, but the ones that I said kind of specific for today are very, very beneficial, just for getting a little bit of a visualization what these terms mean, right? We use the word voltage all the time and don't actually have an understanding of what it represents. Maybe you don't use it all the time. A lot of people do, and we don't actually have an idea what's the difference between current and voltage. Oh, don't go crazy. Okay, so what your work is today? Oh my gosh. Is those next questions. Why is it such a not friend? Okay. Oh my gosh. Hopefully you can see what I'm really trying hard to show you. I'm like having a light panic attack that this isn't going to record because it's being funky. So you have Ohm's law questions here. So using Ohm's law, solving all of these questions. So think about what it's asking you. I'm not going to try to scroll down. There's 8 questions there. So give those a try, and then again, pop to the key that I gave you guys, or that I sent to you guys, or that I don't think I've posted on D2L, but at least I sent it to you guys via email. If you didn't get it, let me know. Why is it not letting me scroll? Yeah, there's 8 questions there. So double check your answers with the key and make sure that you have solved each of those properly. Once you get going, you're going to be like, oh, these are super duper easy, because it's just asking you to solve for V, for I, or for R. So that's it. That's all. You guys have a great day. Tomorrow we will get going. Our next day, we will get going with electricity and circuits. Thanks, guys. Bye. Oh, fuck. Oh.